I had earlier given you the assignment of using 1/5 and 2/3 as the two fractions for you to practice all of your operations upon fraction. And so I almost feel like I need to be playing the role of a coach a little bit here. I want to walk you through this example, and I'm going to ask you to self-correct. Take a look at the work that you've put forward and play this video a few times if necessary until you can replicate that work. See if you can find out where in your initial assignment you might have made mistakes, correct those mistakes, and then repost it back to the discussion group. I will go on the honor system that when you have reposted that you have practiced this until you can carry out these operations. I'm also going to be encouraging you to use the template that I'm providing for you, because this particular template is one you'll be able to use in your classes. And the more you practice now, the more natural it'll be when you actually get in front of students to work with it. I'll tell you right now, these are my models even, and I still practice the division by fractions piece before I go into a classroom to teach it. I recognize that for a lot of us, this represents a different way of thinking about how we represent fractional numbers, how we operate, and how we interpret the results. And so please take the time to practice this until you feel comfortable with it and that you're comfortable with using the template we're providing. Now, the assignment was to take the fractions 1/5 and 2/3 and then to carry out all of the operations that are possible. And in particular, remember, we have representation, we have comparison, we have addition, subtraction, multiplication, division. So we have this full, rich set of operations that if we can make sense of the number, remember that's always first, we should be able to carry these out. I'm going to be providing now the record of action template so we can take a look at that. The template here is a little bit different. It is, remember, both the object we act upon as well as serving a record of action. So after we've done the operations, this template becomes the record of action. That's kind of a subtle point, but it's something we can do when we teach with sketches. Quite often when we work through operations on a sketch, when we're done, the sketch itself becomes its own record of action. It's rather a nice feature. Our first task is to represent. Now remember, if we cannot meaningfully represent the numbers, we can't operate on those numbers. We can't act upon something we don't understand. So as we think about how this is done, we go about representing 1/5 and 2/3. So let's reread that. Remember, this is our share with line. In our new vocabulary, when we see that, we read it as share with. And so this is telling us to share with 5. Remember, share with 5 and take one of the 5 shares. So here's our magic cake over here. We've created 5 equal parts, and we're playing a little bit of let's pretend again. We're pretending these are all identical, and we are taking one of the 5 shares. Von de Waal would call this a part-whole representation of fraction, very, very commonly used. So in reading this, when we talk about our representation state, we start by sharing with 5, taking one of the 5 shares. We now take a look at the second of the fraction cakes, and we're taking advantage of the fact that we can share a square both horizontally and vertically. Because it's a unit square, this distance from here to here is 1, and this distance from here to here is 1. We're taking advantage of that so that we have equal shares. When we read this statement now, this statement would be read as share with, remember there's our share with line, share with 3, and take 2 of the 3 shares. So you'll see we've created the 3 equal shares. and we are taking 2 of those 3 shares. This is our representation phase. And if we don't go any further than this, at least our students will be able to pass the STAR test at the 3rd grade level, which is, can you recognize fractions when they are presented in the pictorial model? Because this is one of the models that you'll be able to see. If you really understand how to read this, you will know that this represents sharing with 3, taking 2 of the 3, and that this would be the symbol that goes along with it. Again, very much like our numerical fluency model, we are able to represent between symbol, spoken word, share with 3, take 2, or okay, 2/3, I know, and visual. Now, to go beyond that, we have to ensure that the size of each of these pieces are equal. And it's at that point that we start taking advantage of the old baker's trick that I shared with you. So in looking at this, we create what I've been calling the comparative form. And so when we think about the comparative form, what we're doing is we're saying, okay, we've known that this is shared with 5 going across. What do we share the opposite cake with vertically? Well, we shared it into 3 parts. So if we share this cake also with 3 parts, we now have something that is shared the same in this direction and shared the same in this direction. To do the same thing over here, it's already shared into 3, remember, and so we have to share it into 5. When we think about the comparative form then, there's a couple of questions we can ask. The first question is, how many pieces are there of these smaller pieces in this instruction? When we share with 5 and we take 1, and we create the comparative form, we have 1, 2, we have 3 pieces. When we share with 3 and take 2, and we take the comparative form, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I truly hope you're seeing the multiplication model play out here. Because when we look at what we've got that's happening, we think about it, and the sharing with 5 is basically telling us how many pieces there are from here to here. You see, that's where we have our 5 pieces. The sharing with 3 tells us how many pieces we have from here to here. There's my share with 3. So in looking at that, if I wanted to know how many pieces there were in this new cake that we've created when we share with 5 and share with 3, you'll notice that we have share with 15. This is the number of little pieces that we have in here. So when we create the comparative form, let's see what we have going on here. We're looking at this rectangle that we're creating. It's 3 in one direction, and it is 1 in the other direction. Well, where is that coming from? Well, let's take a look. If I have my share with 5 and take 1, and I have my share with 3 and take 2, how big is this rectangle that I've shared in over here? How big is that rectangle? Well, it's 1 by 3, isn't it? And we can see where that's coming from. There's the 3, and there's the 1. So 3 times 1 is the area of that rectangle. And if we ask ourselves, how big is this rectangle? How did we get this 10? Well, we can take a look, can't we? We already know the distance from here to here is 5, and the distance from here to here is 2. So if we take the 5, we multiply by the 2, that is where we're getting the 10 that we're showing up here. And so when we look at this particular model, we'll notice that, yes, it's representative It shows the comparative forms, and it also models an old process that a lot of people will be familiar with, and that's cross multiplication. I recognize cross multiplication has problems in terms of being taught, but the reason that it has problems is people just learn it as a process. They don't understand why it works. When we look at this particular way of laying out the problem, you can see how the very action of creating the comparative form also creates everything we need to understand the cross multiplication process. So this helps us in terms of our ideas of trying to get something where not only is it understandable for our students, but it puts it forward in a way that the parents and the larger culture and the community can help understand as well. So when our kids take this home, if we have someone who's learned the old cross multiply process, they can still help. So when we look at the comparison record of action now, if we're going to say which is larger, our task is pretty easy at this point. We know that this gives rise to 3 little pieces, and this gives rise to 10 pieces. We even have kind of a shortcut way of getting there. 5 times 2 is 10. 3 times 1 is 3. And if we wanted to know how big the whole thing is, we just take 5 times 3. So this really represents 3 out of 15, doesn't it? And this represents 10 out of 15. But if all we're interested in is which is larger, it's pretty obvious. I would much rather have 10 of something that I like than 3 of something. And so that gives us our comparison so that we can make that decision very intuitively. You notice how once we represent, how easy everything else falls into place. So having addressed which is larger now, let's think what we do. We've got our representative form. We know which is larger. And you remember when we dealt with whole number, we use this process of pairwise removal, where we remove the same amount from both sides. Well, let's see what that looks like. I'm going to remove 1 piece from each side, 2 pieces from each side, 3 pieces from each side. We're done. Now all we have to do is figure out what it means. So let's see what that might look like. First of all, how many pieces do we have left? Well, we have 1, 2, 3, 4, 5, 6, 7. And how many pieces were there in the whole cake now? Well, it's 3 in one direction by 5 in the other, which is 15. So we have, of those 15 little pieces, we have 7 that are left after we've performed subtraction. Really, all we need to do now is put this into a formal record of action, isn't it? So as we look at our record of action, what could we say about this? Well, the first thing we could say is we know which is larger, so we'll put that out in front. And so share with 3, take 2, and share with 5, take 1. We've done our representation. We're going to do it, dang it. What is it we're going to do? We're going to do pairwise removal. When we've done it, what do we have? We have a cake that has been shared with 15, and we have 7 of the 15 parts. If you want to do this in a way that might make it easier for those people who are used to common denominators, we can write the representative form, which is we have 10 out of 15. We represent 3 out of 15. We do it, dang it. And what do? We do pairwise removal. And when we are done, we have 7 out of 15. Again, the actions that we're performing on the sketch. It's generating the record of action that we want. And the final record of action using abstract symbols is something that we can get help on if we were to send this home as an assignment for our children to work with their parents or whoever else might be in the home for them to work with. So I hope you're seeing just how smoothly this can work. because the object we're acting upon generates its own record of action. That's kind of a smooth thing when you're dealing with sketching. It's not always possible, but in this case, it certainly is. So when we take a look at this, we now have all of this laid out for us. You can reread this again if you'd like. But when we smush them together, let's go to smush them together here. You can see what we have here. The action is really smushing them together. So let's do that. We're going to take each piece, and you notice how we're moving it from one cake over to the other one. So we literally are smushing them together. And all we have to do is create the record of action. So looking over here in terms of the record of action, we represented share with 3, take 2. We represent share with 5, take 1. The comparative form is over here. Share with 15, take 10. Share with 15, take 3. We are going to do it, dang it, on both sides, depending on whether we're dealing with the representative form or just the record of action form. We smushed them together. We did it, dang it. And what did we get? Well, we get 13 out of the 15 parts, and we can count them up right over here. And so whether we view it in either of these two ways of thinking about it, you'll notice again, the procedure becomes the record of action. You all know at this point that the preferred model for multiplication is area model. So just to review that, remember what 2 times 3 equals 6 would look like. Well, something that's 2 in one direction by 3 in the other direction, and we can count up the pieces. 1, 2, 3, 4, 5, 6. And remember our fact families. That tells us that 2 times 3 is equal to 6. That if we rotate that, 3 times 2 is equal to 6. That 6 broken into 3 parts gives 2, and 6 broken into 2 parts gives 3. If we are looking now at what 2/3 times 1/5 would look like, it should look like something that's 1/5 in one direction and 2/3 in the other direction. Why don't you see if you can imagine what that might look like right now? Did it look like this? Now, we're not looking at the whole thing, are we? We don't have all of that. We just have this little piece in the upper left-hand corner. So when we look very carefully at what that is, we will recognize that it's exactly what we wanted. It's 1/5 in one direction. It's 2/3 in the other direction. And all we have of it, again, is that little piece in the corner. We have 1 here and 2 here. Remember, there's our 1 and there's our 2. So out of the 15 pieces possible, we have 2 of the 15. Again, the representation, the record of action, all of these pieces work together so that what we end up with is our final answer. Now you notice the number of small pieces. The numerator is a rectangle that's 1 in one direction by 2 in the other direction. And look what we have here. There's my 1, there's my 2. So how big is this piece right up here that we're looking at? Well, again, it's 1 by 2, and that tells us our number across the top. How big is our piece on the bottom, the whole cake? Well, we've already done this a few times. It's 5 in one direction by 3 in the other. So hopefully this will remind you of a few things, that if we take 2/3 times 1/5, and we're just using the old school way of multiplication, remember you'd say 2 times 1 is 2, 3 times 5 is 15. We're getting the exact same process, but you'll see that we're getting it with a little more meaning, because now we can picture where each of those pieces come from. There is my 2 times 1, and here is my 3 times 5. Again, same story, isn't it? We're building the record of action so that the result gives us what it is that we're looking for.
I recognize that of the operations we have seen so far on fractions, division is probably going to be the most problematic. One reason for this is that when we divide fractions, it's necessary for us to flexibly redefine what counts as the unit. Let's see if we can make this very clear. When we look at the instructions, share with 5 and take 1, the first thing we have to do is we have to represent. And on the interest of clarity, I'm going to make this look a little bit larger so that we can see it a little more clearly as we start acting upon this sketch. First thing, though, is we want to verify that that is indeed following the instructions to share with 5. There's 1, 2, 3, 4, and 5. And then take or consider one of those shares. So we're definitely in the right ballpark here. I'm now going to represent the other instruction, and the major reason I'm doing this is just to make these a little larger so that they're easier to see. So share with 3, take 2. You'll see we have our 3 equal shares, and we have 2 of them shaded in. At this point, it's important for us to remember that before we can do any other operations, we have to create what I've been calling a comparative form. And what that means is that if we look at how this was shared, it was to share with 5 parts, we also want to be able to show it as being shared with 3 parts. And the easiest way to do that is to simply cut the cake so that it's the same in both cases. And we'll do the same thing for the 2/3. We'll cut this cake also so that it's shared both with 3 and with 5. So let's make sure we have that right. 1, 2, 3, 4, and 5. So once we have it in this form, now it's just a question of thinking about what it is that we are doing with this division operation. And it's helpful for us to note that we have 1, 2, 3 pieces over here, and that we have 1, 2, 3, 4, 6, 8, 10 pieces over here. These numbers become the new units that we are going to be concerned with, because when we think, what does it mean to solve the problem 1/5 divided by 2/3? At its simplest level, that's telling us how many times will 2/3 fit into 1/5. Well, 2/3 gives us 10 pieces. 1/5 will give us 3. If we tried to fit all of these 10 pieces over here, you'll see we couldn't make them all work. They just simply not enough spaces for them to go into. However, of those 10 pieces, we can see that we could move 1 over, we could move 2 over, we could move 3 over. And so we get the answer that it's 3/10, or share with 10, take 3. This should not be a surprise, because if we think back to our traditional ways of solving this problem, you would multiply by the multiplicative inverse. That's the way we used to teach that, in fact. And so you take 3 times 1 is 3, 5 times 2 is 10, and you see we get the exact same answer, don't we? This one has quite a bit more meaning behind it, but we still have a process that we've generated that we can now send home and can expect for family support. Now, we could do another problem here. As long as we've represented these fractions, we might just as well, and that is, what is 2/3 divided by 1/5? This is a little bit trickier, because what it is asking is saying, of these 3 parts, how many times can we fit them into 10? Well, let's number them. We have 1, 2, we have 3 over here. So let's keep track. 1, 2, 3. So that fits 1 time, doesn't it? So there's once. 1, 2, 3. There's twice. 1, 2, 3. There's 3 times, and one of those 3 will fit again. So that fits 3 full times, and one of those 3 will fit again. Again, this should not be a surprise, because if we think back to the way that this would have been taught traditionally in old school textbooks, we would take the inverse, we would multiply, gives us 10 over 3. We would remember that this is another way of showing division also, and 3 would go into 10, 3 full times, and one of the 3 would be left. So what we can see here is we can see that this sketch provides itself a very nice way of making a record of action, where the record of action is generated in the process of solving the problem. The biggest issue you're going to have here is to practice it enough so that you're comfortable with it. You'll find that your students will grab onto this quite quickly and be able to solve problems quite easily using it. But like most of us, if you learned a different approach, you're going to have to practice it until this becomes your natural way of solving the problem. For whatever it's worth, I have been using this method for years, and I still practice before I teach it to a group of students or to a group of teacher candidates.
When we think about the essential concepts then, working with fractions, it's going to be very, very similar to what we did in basic numeration. First, we have to get numerical fluency. That involves we have representational power. How do we represent a fraction? I've been encouraging you to use the fraction cakes as opposed to circles and Cuisenaire rods and other models, because they're generalizable and because they also tie in to the area model for multiplication and the division model for multiplication that we've been developing. We need to understand what this representation means. That's part of numerical fluency. And we have to be able to compare fractions in a meaningful fashion so we know which is larger and by how much. We have to have a sense of what the comparison shows us, because if we've done all of these things, that means that we have a meaning for this new number type that we can now act upon in a more powerful fashion. In particular, addition, subtraction, multiplication, division. And as we've gone through these steps here, I hope you see that they can be modeled on the template, the fraction cake template, and that the record of that action leads to an abstracted record that's identical to the old school procedures that people of my generation and my children's generation would recognize. Finally, I need to challenge you to make sure that you enable your students to be able to link the sketches and the procedures in your own mind. You can't teach something as a teacher that you haven't experienced as a learner. So please, please, please avail yourself of this opportunity to go through this, to review it, to practice it until it becomes second nature for you. Again, I know this is not probably the way you were initially taught, unless one of my former students was your classroom teacher. That does happen. I've had it happen maybe 50, 60 times in the past 10 years. So it is possible. But if not, please practice this so that it becomes the natural way when you start working with your own students. You will find that not only does it help you with your initial teaching, but it is also extremely powerful to remediate with for those students who may not have learned this way or who transferred into your class partway through the year. Very, very quick able to remediate using this model as well as initial teaching.